This is a short summary for Chapter 6. In Chapter 6, I focus on filterable functors. These kind of functors are not usually presented in the literature on functional programming. I consider them as a separate type class. Usually, filterables are considered as part of monad, in monad filter, so-called, but I treat them completely separately. And this chapter has a title of Computations Lifted to a Functor Context, Part 1, because filterable functors can be already used in a computation involving a for yield block, which I call the functor block. As a first example, I present this computation, and I show that it can be expressed using map and filter. And this is something we already know from previous chapters. And I start with this example to show that this computation can be expressed in a more visual way using the for yield syntax in Scala, which is called usually for comprehension, but I find it not very comprehensible as a term, so I prefer to call it a functor block or a for yield block. I explain what that block does in general and say what a filterable functor is. And the main thing it has, in addition to a usual functor, is the if construction that you can use in the functor block, or a with filter function that is Scala syntax for that function. And this is a type signature. So the main questions are: what are the laws and properties of this filtering operation, and what are the data types that can have that operation? And I consider first examples of option and list. And the main intuition here is that a filterable functor must contain a disjunction that have more or fewer data items of type T. And so when we filter, we may decrease the number of data items held in a container. And if you look at this type formula, then filtering means that we had, let's say, 2 elements and now we have 1, or we have 3 elements and now we have 2. So one of these is replaced by a unit, let's say it is by 1. So that is kind of an intuition. I consider them further examples that usually we would not think are filterable, but actually it's this general idea that you have a container and an operation that may delete some elements from it. And so I give some interesting examples for that. In order to understand what the mathematical laws must be, I consider a computation of some general kind, and I derive 4 laws or 4 requirements that intuitively we should expect this program to have. Now these are intuitively formulated as something that is desirable. Then I formulate them in a more rigorous way as algebraic laws. And I give examples of functors that are not filterable, that cannot have the filter operation satisfying these laws for one or another reason. The worked examples show some descriptions and type formulas for filterable functors. Also, I give an example of a filterable contrafunctor. That is a contrafunctor where the type parameter A is in a contravariant position, and that contrafunctor still has with filter defined on it in a kind of similar way. I give exercises for deriving the filter implementation for various situations. As the second part of chapter 6, I now consider the laws of functor that is filterable and try to formulate them in an easier way, because there are 4 laws and there doesn't seem to be an easy way of understanding why there are 4 laws and not 6 or 14 laws. Actually, some presentations of filterable functors that I could find online have different laws. And so in order to understand what laws are correct or reasonable, we need to reformulate the laws in a more elegant and mathematically reasonable way. So that's where I start. I say, how do we replace by one, by unit? So if something is filtered out, our intuition was that it's replaced by a unit. Now we could replace it if we actually had a disjunction type that had a unit as one of the parts of the disjunction. So this is, in other words, an option type. And that motivates the formulation of the laws in terms of the operation called deflate, which has this type signature. And I show that deflate can be defined through filter, and filter can be defined through deflate, where the BOP is an auxiliary function that converts a Boolean predicate into a function of this type. I explained that deflate and filter are computationally equivalent. In other words, one is defined through the other, and these definitions are equivalent. And deflate is actually much easier to reason about because its type signature is much simpler. Now, the interesting thing about deflate is that if filter is defined via deflate, law 4 is satisfied automatically. I explain how that works in a detailed derivation. I give a type diagram for how deflate operates in law 4. I explain how to read this diagram and how to simplify these kind of expressions. And finally, I show that deflate is a natural transformation. I explain what that means. If I rewrite law 1 in terms of deflate, I get a law that interchanges deflate with fmap, and that's a naturality law. I give an intuition for what a natural transformation is and some examples. Now we can use a naturality law and show that law 4 is satisfied automatically for a filter. This is the derivation that I show in the lecture. Now we are down to 3 laws, but we seem to have this composition. Psi p was an auxiliary function defined previously. We seem to have this composition often. So what if we define a new function through this composition? And this new function I call fmap opt, which is kind of fmap, except the signature of the function f is not a to b, but a to 1 plus b, or a to option b. I show that fmap opt is equivalent to deflate, and if I expressed laws 1 to 3 in terms of fmap opt, and I introduce some notation, the diamond symbol with an opt subscript, which can be seen as a composition of 2 functions, except that functions have this twisted signature. Instead of A to B, it's A to 1 plus B, and instead of B to C, it's B to 1 plus C, and their composition cannot be done normally, so it's a kind of a twisted composition, and I explain how that works. I call this a Kleisli composition. It turns out that in terms of Kleisli composition, these functions have an associative composition operation with identity element as well. And so the fmap opt lifts this kind of function into the functor f, into functions fa to fb. And it turns out that fmap opt only has two laws, and these two laws are strikingly similar to functor laws. They're identity law and composition law, just like lifting, except for the signature, which is A to 1 plus B instead of A to B. I explained that these are equivalent to old laws, so I derived them from the old laws, and I now derive the old laws from these two. So this is a derivation. Finally, I summarize to say that these two laws for fmap opt are similar to the functor laws, except that the function signatures are twisted, so to speak. And I explain that category theory generalizes the definition of functors, and in this way we can see this as a functor lifting map, similar to the other lifting maps, as long as the types have been twisted in the right way. And I comment on category theory that gives us this generalization, and yet has limitations as to what you can prove from pure category theory, as opposed to proving things by hand, as I have done in this tutorial. Now that we understand the laws, let us find out what functors are filterable. And the way to do it is similar to how this was done for ordinary functors. Namely, we try to find constructions that build new functors from old ones and keep the property that we want. And the property right now is going to be that they're filterable. So for example, if two functors are filterable, then their product is filterable, their disjunction is filterable, their composition as functors is filterable, and there are other such constructions. And I give example code for this and demonstrate that the laws hold using tests for each of these constructions. In the worked examples, I show a symbolic derivation of some of these laws, such as for these, if for these functors fa and ga the laws hold, then they also hold for their product. And I use the fmap opt laws because they're just two, and it's shorter to check that the laws hold. So I give three constructions that I derive in detail. And I show that different kinds of filters, including list-like filter, can be derived as a general construction. Using these constructions, we can now take some complicated type expression like this and find that it is filterable and implement automatically just by following the constructions and splitting this type expression into parts, finding in each case what the step is that build a bigger functor from smaller ones. And I give exercises that are similar to the worked examples that I gave. As a bonus, I show the properties of filterable contrafunctors. I do not derive everything in detail, but these properties are very similar to the properties of filterable functors, and their derivations are exactly similar, except that some of the arrows will be reversed. The type signature of the filter is the same, but the deflate function needs to be now replaced by the inflate function with this type signature. And fmap opt needs to be replaced with a contra fmap opt with this type signature. And there are very similar properties, the computational equivalence between filter, inflate, and contra fmap opt. The laws, that filter has 4 laws, inflate has 3 laws, and contra fmap opt has 2 laws, just like in the case for functors that are filterable, where filter has 4 laws, deflate has 3 laws, and fmap opt 2 laws. I give some examples of filterable and non-filterable contrafunctors. Then I again consider constructions. If I have previously found contrafunctors, what are the new contrafunctors I can build from them? And these are the constructions. Then I give some notes in the slides that I did not mention in the video.